we're here for lecture 20 on the proof complexity as a computational lens course. So far, we talked about resolution, we talked about polynomial calculus. And so the development is, I think, for resolution, we had several lower bound strategies. We started with prosecutor-defendant games. Then we did some work with random restrictions. We finally got to the size-width relation and realized that we had suffered a lot and could have suffered a lot less by just proving strong enough width lower bound and using this general theorem that says basically that general lower bounds on resolution refutation width implies exponential lower bounds on resolution refutation size. But there was a whole repertoire of proof techniques. For polynomial calculus, there was this analog where there was a size degree relation, and we pretty much used that all the time. So much more limited menu of options. We did random restrictions when we established this tight relation that somewhat low degree polynomial calculus refutations can be maximally large as their degree allowed. But other than that, it was mostly degree was pretty much the only game in town. Also, we did last lecture, Kilian did size lower bounds for the +-1 basis. And again, this all boiled down to degree lower bounds in the end. Now we're going to talk about polynomial calculus. And there it turns out that the menu has been even much more limited. For a long time, there was basically only one technique that was interpolation, which we did a warm-up early on in the course for resolution. Now we're going to revisit interpolation again. So this is basically just taking our proof complexity lower bound and translating into some kind of circuit complexity lower bound. Now we hope to cover, as we hope to show in the following lectures, in the last few years, there have been some pretty exciting developments for cutting planes, so that there are now more available techniques. So next lecture, we will show that some kind of bottleneck counting technique that is in some sense similar to what we did in the very first lectures can be done also for cutting planes. And then one very powerful technique that we will see in, I think, early February is lifting, where we basically reduce questions about cutting planes proofs to communication complexity, where parties need to communicate and computation is for free. The only thing we pay for is how much they need to communicate. But today we're going to talk about cutting planes. We're going to recall what cutting planes is. We're going to recap what interpolation is, and then we will try to prove a lower bound on cutting planes using interpolation. So cutting planes operates with 0-1 integer linear inequalities. Sometimes I will refer to them as pseudo-Boolean constraints. Just if I happen to accidentally say that, that's what practitioners will tend to say. So, but we define our proof system as operating with CNFs. So let's just recall that if I have a clause that looks something like this, so I have a bunch of positive literals, x, and a bunch of negative literals, y, then I can translate this clause just by summing up all the positive literals and summing up 1 minus the negative literals and saying that this should be at least 1. Now I think of 1 as true and 0 as false. We're not going to change this now. We decided that 1 is true, 0 is false. Recall that for algebraic proof systems, we were a bit schizophrenic about this. Now we've decided, committed fully, that 1 is true, always. And if we just massage this a little bit, you realize that this will just be plus all the minus y's, and this is going to be 1 minus the number of negative literals. Okay, so this is somehow implicitly our first step. Whenever I think about what cutting planes does to a CNF formula, so in our head, we automatically run this translation. And that makes cutting planes into a proof system for CNF formulas. Cutting planes makes excellent sense also for more general 0-1 integer linear inequalities, and we'll use that later today. Okay, so we can think of the inputs as being clauses in this form, or more general 0-1 integer linear inequality. What derivation rules do we have? So we have variable axioms. We can always, at any point, assert that x lies behind 0 and 1. And let me insist, as long as I have the energy, we'll do greater than or equal to constraints. So that's x less equal 1, I'll write it in this form, just to have the greater equal. Okay. Then we can add two constraints. So if I have ai xi greater or equal a, and I have bi xi greater or equal b, then I can just add them up. So summing up ai plus bi times xi is then clearly at least a plus b. If these two qualities are valid, multiplication says I can multiply by a positive integer. Multiplication is hard to spell. Let me make a second attempt. Multiplication. Again, if I have summing over ai xi greater or equal a, and suppose that c is a positive integer, then obviously it should hold that c times ai xi greater or equal c times a. Okay. So far, we're basically just operating. Note that everything we did so far is valid also for real valued variables between 0 and 1. So you can view this, if you wish, as like a proof system for linear programming. We're not going to solve any Boolean problems in this way, because there's no way of, again, if we have a bunch of inequalities that have a rational solution, then, okay, so what is our goal? Our goal is to take the axioms and apply the derivation rules, and we want to refute things. We think of a refutation as, what's the empty clause? If you run this translation on the empty clause, it will just give you 0 greater or equal 1. So we think of 0 greater or equal 1 as contradiction. And cutting planes proof of unsatisfiability is you start with a bunch of inequalities and you derive 0 greater or equal 1. Except if our set of inequalities has a rational solution, then these rules will not remove that rational solution, right? Because they're all valid. So we need some kind of Boolean rule. And here there is some flexibility. Usually how it's defined cutting planes in the proof complexity literature is you say the following. Suppose that c is again a positive integer, and suppose that all the terms on the left-hand side have a common factor c. Then clearly I can divide through by c. C is again a positive integer. So I divide by c and get a I times x greater or equal a divided by c. And now the point is that this need not be an integer, but I know that this one is, so therefore it's safe to run. And now we have a Boolean proof system, and we're not really going to show this, but it turns out that if indeed you have a set of 0-1 integer linear inequalities that defines a polytope without integer points, then with these rules we can derive 0 greater or equal 1. Okay, so it should be clear that these rules are sound, but they're also complete. And something slightly stronger could be said. With these rules, if I have a bunch of inequalities and they imply semantically some other inequality, then in fact there is also a syntactic derivation of this inequality. So this is what is known as implicational completeness. That you can refute something that is unsatisfiable, that's refutational completeness, but cutting planes is slightly stronger, it's implicationally complete. It's somewhat similar to for resolution. If a set of clauses implied any clause, then we could also derive that clause or a subclause, and there's a corresponding thing that holds for complex. So this proof system, where does it come from? Well, it was introduced by in 1987 by, okay, so I'm blanking already, Blackboard syndrome, that's not good. CCT 87 is the paper, which is Cook, Couillard, and Turan. And it was meant to model zero-one integer linear program. But if you're doing, and in the context of zero-one integer linear programming in operations research, division is more often known as Quatal-Gomori cuts. But those we usually write like this. So let me write a more general division rule. This would be something like the following: that I know some AI xi greater or equal a, and I know that c is an integer. Then I just divide through everywhere. AI divided by c times x, sum over I greater or equal a divided by c, and then I just round up everywhere. Okay. And so whenever we want to, I think for sort of if you want to be close to algorithmic applications, then actually this general division rule is slightly nice. It doesn't really matter. You realize that, well, if you can derive something with general division, then with at most a linear number of steps, you can also get the same rule with standard division. And basically, how do you do it? Well, you just add enough constraints x greater or equal 0 to these coefficients until they are divisible by c, and then you apply the standard theoretical computer science division rule. So it's like you can pick whichever of the rules you like. Actually, yeah, so okay, that's what I wanted to say about this. For now, there are also other possible rules, but we will talk about them in a minute, I think. So now I want to say, so there's just a few facts that we're not going to prove. They're not hard, so maybe we'll mostly leave them as exercises. So cutting planes efficiently simulates resolution. What I mean by this. So first I should define complexity measures, I guess. Just as for resolution, we can define a derivation is just a sequence of linear inequalities. So I want to count length, then I'm just going to count the number of such steps. Okay. And then it's not so hard to see that if I have a resolution refutation of a CNF in L lines, then big O of L lines, or in fact, if I allow the general division rule, then I think it will be almost like actually L lines, maybe except for some additive constant. You can simulate. Cutting planes can simulate the resolution refutation step by step. For cutting planes, we also care about size. Then you count all the bits of the coefficients. It's an earlier result that, in fact, without loss of generality, coefficients have at most exponential magnitude, meaning at most a polynomial number of bits. So length and size are not so far from each other. That means that if I give you any refutation with ridiculously large bit complexity, you can massage it with at most a polynomial blow-up to get smaller coefficients. Space, we're going to talk about that in a few lectures. Again, our space measure tended to count the number of things in memory at the same time of the type of object that we measured for length or size. So here, the most natural measure is line space, which is counting, if I give a configuration style derivation, how many linear inequalities do I need in memory at the same time? And then it's not so hard to see that, again, if I just run the natural cutting planes derivation that simulates a resolution derivation step by step. Also, the line space for cutting planes will be exactly the closed space. Okay. So I'll leave that as an exercise. So this means that cutting planes is at least as strong as resolution. Anything resolution can do, cutting planes can do, but in fact, cutting planes is exponentially stronger. So with respect to length, stronger than resolution with respect to length. Look at the pigeonhole principle formula. So this is a nice exercise, but basically in cutting planes, what you can do, what the pigeonhole principle formula says, really fix a pigeon sum over all holes. The sum is at least one, the pigeon goes to at least one hole. And then you say fix a whole sum over all pigeons, then this sum is at most one. Okay? Or you pull this trick so you get a bit summing over all, fix a whole and sum over all pigeons, then minus the sum of all pigeons is at least minus one. So every hole takes at most one pigeon. And the point is, I'm going to leave this as an exercise, but even if I give you the CNF formulation, you can just massage these clauses and apply division to recover the representation with linear inequalities or so-called cardinality constraints. And once you have these cardinality constraints, it's not too hard to see that if you just sum them up, then all the variables will cancel and you're left with 0 greater or equal 1. So in fact, cutting planes, we won't do the details, but so the pigeonhole principle we know is exponentially hard for resolution, but cutting planes, even with a tree-like proof where you don't use any intermediate results more than once, can refute the pigeonhole principle. Okay, does this make sense? I'm skipping the details, but they're not hard. So just because it's fun, let's look at another example for this. So, because I think these formulas are interesting. So even coloring formulas, I think they were invented by Claes Markström in Umeå, as far as I'm aware. So the point is you have a connected undirected graph. With an Eulerian cycle. What does that mean? It means that all vertices have even degree. Okay. And now you let so the variables are just the edges. So an edge E is the variable x sub e. And then for every vertex, you get a constraint. That says basically the following. Okay, so one piece of notation that we're going to use is just syntactic sugar. Sometimes it's convenient to write the constraint sum ai xi equals a. And that is, of course, just syntactic sugar for summing ai xi greater or equal a, and then summing not ai xi minus ai xi greater or equal minus a. Okay. Sometimes we'll just use this syntactic sugar, and this is just really, I view this as an abbreviation of these two inequalities. Okay. So then the vertex constraint will say for every vertex, let's look at all the edges incident to that vertex. And you sum up all these edges, and the vertex wants to see that exactly half of them is true. And this is a constraint that is better if, like, the degree is an even number. Okay. So now it's not so hard to see. Let's write this down. That the even coloring formula, which I'll write ECG, is is unsatisfiable, assuming now that, again, G is connected, all vertices have even degree. So the formula is unsatisfiable if and only if the number of edges is odd. And if it is unsatisfiable, then again, tree-like cutting planes, cutting planes refutes the even coloring formula efficiently. Okay. So the point is, okay, so let's get the proof of this. Suppose first that the number of edges is even. So there is an Eulerian cycle that visits all the edges. And it's an even number of edges. So just fix a start vertex, start walking your Eulerian cycle. As you walk, every second edge you set to true, every second edge you set to false. Okay, so now clearly for any vertex that I visit, I set one edge to true, say, coming in, but then I set another edge to fall coming out, or the other way around. Is it clear that if I just walk an Eulerian cycle and set true, false, then this is going to be a satisfying sign. Now, suppose that the number of edges is odd. And again, let's just see that we have, let's do one direction of this. So look at all the greater than constraints. Okay, so we have this constraint for every vertex. So if we now sum over all vertices, then what do we get? Well, we're going to count every edge exactly twice, right? So we get 2 times on the left-hand side, we get 2 times all edges, xc. Greater equal. What do we get on the right-hand side? Well, we get sum over all vertices, the degree of the vertex divided by 2. Yes? Okay, but this, if you think about it, this is just the number of edges. Right? So now, if the number of edges is odd, we divide, and we get that the sum of all edges is at least the number of edges plus 1 divided by 2, because we round up. And now, if you do exactly the same thing, but for the less than or equal constraints, then you will derive that actually the sum of the edges is at most e minus 1 divided by 2, and then you sum them up and you get a contradiction. Does it make sense? So then in terms of lower bounds, we know that suppose, okay, yeah, I should have said, sorry. So just, good. So let me talk about, I'm cheating you a little bit on the details. So let me first do the back up like 3 seconds to make sense of what I said. So here is, it's hard to do a small cute example of the even coloring formula. So this one is in particular has an even number of edges, so it will be satisfiable. But just to say, so suppose you have a graph like this, and the edges are u, w, z, x, y, v, then these 2 clauses say that here, this vertex wants to see one of these guys true. Down here, this vertex wants to see one of u and z true, etc. Here over on the right-hand side, this vertex wants to see exactly 2 of w, x, y, and z true, and that's these 4 clauses say that at least 2 of them are true, and then these 4 clauses say that at least 2 of them are false. Now, again, it's not so hard to see that if you just take this, and this is how I wrote this, then yeah, from this encoding, I can recover easily that u plus w is 1, u plus z is 1, b plus x is 1, b plus y is 1, and then w plus x plus y plus z equal 2. Okay. So in fact, we can be a little bit schizophrenic, like either I give you the formula in CNF, or I could even give you just this encoding. And when I sketch this proof, I somehow implicitly assuming that let's recover the cardinality constraint and then do this reasoning. Let's skip this step. Went a little bit fast. Okay, so what do we know in terms of hardness? So I think the for quite some time, like at least since 10 years back, I and maybe others also have made the argument that if you think about what we did, like the Benson-Wigderson framework, it should be possible to use this to prove linear width lower bound for even coloring formulas. If you take an expander graph of large enough even degree, like if you take a 6 regular expander with an odd number of vertices, then the number of edges will be odd. Or you take if that expansion will not be good enough, like take a 10 regular expander or something, again with an odd number of vertices, then you'll have an odd number of edges. And for 6 or 10 or at the very latest 14 or something, you should be able to get a strong width lower bound. You have to work a little. It's probably like a good exercise to actually write down the details, but basically, if you do this carefully, you should get Benson-Wigderson to work. Okay, except that I don't think anyone wrote it down. So what has been written down is by Kilian, Risse, and Per Austrin. They got this as a corollary of a much more general result. So basically what they say that take an expander G of large, like very large, constant degree. So it's an expander, very large constant degree. We want number of edges odd. We want the degrees even. Then resolution requires length exponential in n, except that for annoying reasons, there's a log n factor loss, which shouldn't really be there, but it's from their proof technique. So there are, the log n shouldn't be there, and we shouldn't need a ridiculously large constant. But this is what is there in the literature, and working this out just with your bare hands for resolution to get a lower bound for like 6 regular or 10 regular graphs would be a nice thing to do, and get rid of the log n. But anyway, the point is that this shows 2 examples. So the pigeonhole principle formula, which is a counting example, even coloring formula, which is more like an even odd counting principle. Both of them are dead hard for resolution and absolutely trivial for cutting planes, which shows the power of counting. Okay, so now I want to make a small detour. So questions about this so far when I clean the board? We're happy with this? So we said that we have a computational length of proof complexity. And now we've seen we have a proof system that is at least as strong as resolution, but can do exponentially better. So then it's natural to ask whether we can use this for SAT solving, or since we're doing it for 0-1 interlinear linear inequalities, this is called pseudo-Boolean solving. can we somehow leverage the power of cutting planes to get better solvers? When you ask this question, it is relevant to introduce some new notions. So firstly, it is kind of nice to write your inequalities in normalized form. Namely, normalized form is I write my linear inequalities as positive linear combinations only, but then I allow literals. So my inequalities now look like Li, Ai, sum over I, Ai, Li greater or equal A, and all the coefficients and the right-hand side term, they're all positive. And when you write it like this, A is sometimes referred to as the degree of falsity or just the degree. Also, when people started to build pseudo-Boolean solvers, they actually used another rule, which is called saturation. And saturation is the following. So suppose I know Ai, Li greater or equal A in normalized form, importantly. Then we claim that actually, if there are some coefficients here that are larger than the degree, then we can just cap them. So for every xi, you can just multiply it by the minimum of ai, little ai, or capital A times Li. Okay? And the reason for this is that, well, either the inequalities is already satisfied before I reach Li, and then I don't care. But if nobody else is contributing and Li has to do all the heavy lifting, still, in order to reach A, we don't need more than A. Okay, but obviously this crucially uses the fact that you have normalized form. Otherwise, it wouldn't be true. Okay, so this is a rule that has been used, and also for algorithmic reasons, it's natural to think not about addition and multiplication separately, but it's natural to think of taking linear combinations. So if I have some ai xi greater or equal A and some bi xi greater or equal capital B, then I can multiply by ci and cb, both being positive, and derive the linear combination ca times ai plus cb times bi xi greater or equal ca a plus bb. And we say that a linear combination is canceling if a variable vanishes when you take this linear combination. Okay, so a canceling linear combination is when I add them up in this way, some variable vanishes. And now you realize that the way we would simulate resolution, if you think about it, then sort of the resolution step is exactly just adding up x and not x so that they cancel. And it's important to realize also in normalized form, I should have written this down, that when you have normalized form, you take x and x bar. What does it mean to cancel? Cancel means that they both vanish, but they leave a 1, right? Not a 0. This is obvious, but it's good to think about because obviously either this guy is 1 or this guy is 1, and then the other one is 0. So now the interesting thing is that just as in SAT solving, you use the resolution rule. Why? Because you tend to look at pairs of clauses when they have different opinion about the variable. And in the same way, if you try to lift this algorithm to cutting planes, then you tend to look at two different linear inequalities when they have opposing opinions about the variable. So therefore, pretty much all the algorithms I'm aware of only do canceling linear combination. Not general linear combination, but canceling. Okay, and then there's a choice, do we want to use division or do we want to use saturation? Then you can say, I want to use both. But somehow, often they do not necessarily commute. And for reasons that also we don't really have time to go into this, but sort of you have to commit to which rule you like the most, and they don't always play well together. So therefore, it's natural to somehow think of, in terms of proof systems, there have been solvers that use basically only saturation and solvers using only division. And this gives rise to a natural theory question, namely, which Boolean rule do I have? And which kind of linear combinations do I do? Where I can say for my Boolean rule, the first solvers use saturation. Later solvers have started using division. I guess this was pioneered by this research group. And then, as I said, algorithmically, pretty much all solvers do canceling linear combination, but you can also ask, what if I have linear combinations without any restrictions? Okay, how does this affect? Like now you realize I have like 4 different proof systems here, 4 different flavors of cutting planes. Am I making sense? Then we can ask, how do these relate to each other? Okay, so what is known? So first, observe that over here we have standard cutting planes. If I have, as defined in the theoretical computer science literature, I have division and I have general linear combinations. So whenever I want to simulate additional multiplication, I can do it without any problem. And this is, again, as I said, I didn't prove it to you, but this is implicationally complete. Okay. Then it's probably folklore, or going back to like, late 80s, early 90s, that suppose that I insist on canceling linear combinations, and suppose I insist on the input being in CNF, then it's not so hard to see that this is just a complicated way of describing the resolution proof system. Because if I start with clauses, the only meaningful way that you can do canceling addition is sort of simulating resolution steps. And now after this, the only thing that can happen is that some coefficients are 2 instead of 1, and then saturation can saturate them away, but then you get another clause. Division, you can also divide by 2 or something larger, and if you do that, you again get a clause. So you can only generate clauses, and the only way you can generate clauses is by effectively using the resolution rule. I mean, you need to write it down a little bit more carefully, but it's really this, nothing more. And this is, by the way, also a problem that pseudo-Boolean solvers struggle with today, which is very annoying. Like if you want to kill a pseudo-Boolean solver, give it a CNF input. Very annoying. So if we want to use pseudo-Boolean solvers, you're doing it because you have a better 0-1 ILP encoding in mind. So interestingly now, it's okay. Suppose I now have no restrictions on my linear inequalities, but I insist on using saturation. Then the first funny thing that happens here is that this is not implicationally complete. So I can always, it is refutationally complete, which is not so hard to show, but it's not implicationally complete. So maybe I should say that this is refutationally but not implicationally complete. And this is not so easy, but it can in fact be shown that if I insist on CNF formulas, then the fact that I allow you general linear combinations doesn't really help. This is still essentially a resolution. Okay? In the sense that clearly saturation with general linear combinations can now generate things that are not clauses. That's, so it can't be an equality in the sense that it's over here. But if I have a refutation in saturation with general linear combinations of a CNF formula, then you can do it in the same length, essentially, in resolution. And this is already complicated enough to, I guess, write down as a theorem. So this is by Vinyals et al. And then a follow-up work by Gocht and myself and Amir Yehudayev. So both from this group. And this means now that division in general, cutting planes with division and general linear combination can be exponentially stronger than saturation with saturation with general linear combinations. How do we know this? Well, again, take a CNF formula such as this take an even coloring formula or pigeonhole principle formula in CNF. What cutting planes with division and general linear combination will do, it will recover from the bad CNF encoding, and then it will run the short cutting planes proof. Cutting planes with saturation cannot do this, provably. And so it's stuck with doing the resolution proof. So this means that, okay, now we know that cutting planes with division can be exponentially stronger than cutting planes with saturation, except that this is a little bit ridiculous. You're sort of saying, yeah, but what if I... So firstly, this cardinality recovery is using general linear combination. Algorithmically, we would do canceling linear combination. Okay? And now you realize that, so I'd like to actually separate these two guys, and now I can't separate them with CNF formulas because they both collapse to resolution. So the question is, like, algorithmically, it's interesting, cutting planes with saturation, cutting planes with division, but I insist maybe on canceling linear combinations. How are they related? And this is actually not fully understood. Okay, so let me tell you what is known, that cutting planes with division and canceling linear combination, it can be exponentially stronger than cutting planes with saturation. And for saturation, you kind of... actually, here I don't care if you have general linear combinations here. And this is, again, so all of these later results are from Gocht, Nordström, Yehudayev. So this can be exponentially stronger than this. What about in the other direction? Well, what we know there is that an individual, there are like derivation steps, very neat derivation steps that I can do with saturation. That can require an unlimited number of division steps. Okay, but this just tells me, and we'll see this in a second, but this sort of tells me if I give you these constraints and you have to derive exactly this constraint, then saturation can be more efficient. But we don't know. So what is open is whether cutting planes plus saturation, can it be stronger than cutting planes plus division for refutations? This we don't know. Okay, and this saturation thing is also the go at all. So we'll soon move on to interpolation, but I just wanted to say, I think these are nice problems. And I just wanted to say, like, give you a flavor of roughly how they go. No proofs at all, but just sort of, one of them is just a stupid trick. And the other one is, I think, more interesting. Okay. So as we said, we cannot use CNF formulas to separate cutting planes with division and cutting planes with saturation. Except, what do we do it anyway? By cheating. Okay. Suppose I have, just as an example, suppose I have this literals 1, 2, 3, 4. Sum them up, and there are at least 2. These are actually, these are the kind of constraints where, when I do even coloring formulas, or sort of, if I generalize it a bit, for say pigeonhole principle formulas over graph pigeonhole principles, these kind of constraints could already help a lot. Okay, but I cannot. So suppose now I obfuscate them in the following way. Okay, sorry. I wanted to write this. Suppose I obfuscate them in the following way. Actually, this one. Something slightly off in my notes. Let's see how this goes. I think we can sort of say what I want to do, but it seems that there's something wrong. Or maybe it is. Let's see. So basically, I want to write something like this, but I'm going to obfuscate it. Yeah, my coefficients are a little bit, I don't know. Anyway, so the point is now, if I sum these up, then, okay, there's something wrong here. But basically what will happen, let's see if we can figure out the math. So I wanted to write something like this, but I'm writing these constraints instead. Okay, and now if I sum them up, these just cancel, and then we'll leave something like a 3 down here. And here I get 3 times L1 plus L2 plus L3. And then I think I messed up my right-hand side, probably. Maybe let me throw in the 2 somewhere. See if that will fix it.
So in the Nordström paper, you have the 2's on the not 3 constraints, but there you have 4 literals instead of 3. So I'm not sure if that.
Yeah. So what? That's when I lost the 4th literal. So
1 at the first one and 2 at the other 3 should be fine.
what should I do? I should L1, L2, L3 greater or equal 1.
Yeah.
And then what do I do?
Then L1, L3.
But where does L4 come?
Oh, basically, but like greater or equal to
L1, L3, L4.
If we take from the paper, L2, L1, L2, L4.
L1, L2, L4 greater or equal to.
Then L1, L3, L4.
Plus L3 plus L4
Greater equal to. Yes.
greater or equal to. And then the final one is
L2,
Z bar
L3, L4.
plus L2, thank you, L3 plus L4 greater or equal to. Good, so now we're going to sum up, we're going to get a 7. Excellent, so now we're in business. This 3 cancels this 7, and we get a 4. Okay. And now the point is saturation is stuck at this point. But if I have division, I will just divide to get L1 plus L2 plus L3, and I'm missing L4, so let me throw it in. It'll be here somewhere, I guess. L4. Greater or equal 4 over 3. Rounding it up, that's a 2. And now you have to prove that. So basically, I wanted this, and I obfuscated it in such a way that now you have to work and you have to show that saturation cannot recover from this encoding, and this requires an argument that I honestly don't remember off the top of my head. But clearly, cutting place with division can do it. So basically, you take a formula where the CNF encoding is bad, but where you can recover good cardinality encoding, and then you obfuscate the cardinality encoding in such a way that saturation cannot recover, but the division can. Okay? Sorry for messing this up. So in the other direction, let's see if I can get this right then. So to show that saturation is stronger than division, we have to be honest also. Also, I mean, clearly one thing I could do, I could give you a constraint with like completely wild coefficients, and then I could saturate it in one step, and division will struggle to do this. So note that, but that's, so I somehow want to start with fully saturated constraints, because otherwise I'm cheating. And we know that division will, so we know that saturation, there are examples where saturation cannot simulate division, period. Division will always be able to simulate saturation, because it's, I mean, cutting place with division is implicationally complete. But the question is, how efficient is the simulation? And the answer is not necessarily very. Okay? So now, to see this, let R be some really large integer. And now consider the following 2 constraints. Rx plus Ry plus summing of R Z variables greater or equal R. So either X is true or Y is true or all of the Z's are true. And then write down Rx plus R not Y plus I goes from R plus 1 to 2R that I greater or equal R. Note that I'm not cheating both of these. We're starting with constraints where the coefficients are less equal than the degree of falsity. So now I can add these with a linear, canceling linear combination, which I have to do because I'm in this column. And when which is also, by the way, I didn't say this, this is something called general resolution, because it's sort of somehow generalizing resolution, or generalized resolution. Okay, so let me add these 2 up. Well, then I get 2 times Rx. The y's cancel and leave an R. Here I get R plus R minus the R that cancels. So here I have R. And then I sum up all the z's. I go from 1 to 2R, Z up. But now notice that this coefficient is really large. But if I have saturation, obviously I just saturate and get this. sorry, this is, let me call this constraint 1, constraint 2, intermediate constraint, and then constraint 4. And now the theorem is that deriving 4 from 1 and 2 requires essentially square root r division steps. Anything else you want to do is for true. You can multiply freely. You can actually, this is also like you're over here now. You can use even general cutting planes if you wish. But you're starting with these two and you should derive this. And then I don't charge for additions. I don't charge for multiplications. I will charge for division steps, and you'll need essentially square root r division steps. And this is interesting in the sense that for most of the cutting planes lower bounds that we will see, we're not able to really argue about the syntax of the Boolean rules. Where all the lower bounds that we do will basically just say, the only things we're assuming for cutting planes is that we have two constraints, and then we combine them and derive a third constraint that is implied by the other two. Okay? But clearly, if we have that model of cutting planes, we'll not be able to distinguish between which implicational rule we're using. So here we somehow need to in much finer detail understand which syntactic rule we're using, and we really don't have those tools. So just to say maybe but here so we develop like a very ad hoc tool that can somehow distinguish if you want to go from these two to this, that actually this requires a lot of division steps, but clearly only one substitution step. And the point is that basically what you do, you say, okay, suppose we have a derivation that starts with these two, and then derives tons of stuff and finally has this. It's a general cutting planes derivation. Then clearly any such constraints I can write on the form A. So the line Ci, I write that Ai times x plus Bi times y plus Ci times not y, where at most one of these two will be, I mean, one of them is 0 and the other one is non-negative. So I'm writing them in normalized form because it's nicer. And then I will have plus Dijzj greater or equal Ai. Okay, every line will look like this, yes? Okay, so now I just want to measure how good or like what kind of potential does this line have? I'm going to define the potential of Ci to be 2 times Ai plus Bi plus Ci. So I know 2 times Ai plus whichever of these is non-zero. And I divide this by the right-hand side. And then let me take the logarithm. And this is somehow a measure of this line. Okay, and now what can we prove? Well, it turns out that the starting constraints one and two, if you do the math, they have the potential, the natural logarithm of 3. Constraint number 4 has potential that is the logarithm of 2. And then we prove that addition and multiplication does not decrease the potential. This is not exactly, there are some corner cases in the proof, but like the moral is that we just show that addition and multiplication, you first sort of, you take care of some very weird special cases of how these look like. And then when you've taken care of those, you just say that, okay, addition and multiplication will never decrease the potential, which requires an argument, but it's not so hard. So our only hope is division. And then you say that division can decrease the potential by, it can decrease the potential, but not by so much, but essentially by 1 over square root of. Okay, so now we're done, because we need like a constant decrease.
It seems like in the potential that you're not really using it, you have these set j's, but like if you would leave them out completely, then
I cannot. Yeah. So yeah, a very good point. So I would like to leave them out completely, but I can't because they're gonna take care of this sort of cleaning up to get the proof to work. So for instance, it would be super nice to because on the one hand, what can we say about the strength of this result? So the way to pitch it, obviously, if you want to say that, look, this says that division has like unbounded inefficiency when it comes to simulating saturation. Like a single saturation step requires an unbounded number of division steps. And note that this is square root r is actually exponential in the bit size of this guy. So like it's a constant versus arbitrary exponential group. Okay, on the one hand. On the other hand, you can say, yeah, but hang on. Like what is the size of these guys, of these constraints? Well, they're of size r, right? So in terms of the size of the objects, this is a very weak separation. It's a sublinear separation, if you measure in that sense. So now you can say it would be nicer to make this stronger, and one way to do this would be to replace this by an exponential sum, for instance. But this, I think, doesn't work. Or at least we weren't able to get it to work. Okay, so open problem. This shows that saturation can be stronger, but again, I want to stress: can we cook up some kind of system of 0-1 interlinear inequalities where it's actually somehow crucial to derive constraints like this, and then use saturation to get them down? Or is it the case that somehow, actually in practice, I mean, if you could do this kind of simulation, then I mean, an extra linear factor is fine, right? But this somehow tells us that if cutting planes with division can simulate cutting planes with saturation, it's not clear what this simulation is going to look like, because like a local simulation doesn't seem to be very, like our simulations usually just go step by step, right? And this doesn't seem to be such a great idea. But I really don't know whether cutting planes with saturation could be stronger than cutting planes with division. The other thing I also mentioned, like these are hard questions because we don't have the tool to distinguish between different syntactic rules in cutting planes. And this would be interesting also because if you, saturation and division are two examples of so-called cut rules. And the operations research literature has tons of cut rules. And basically you can define different cutting planes flavors with different cut rules. And it might be interesting as a proof complexity study to understand how strong different cut rules are. In terms of really, I mean, there is a study of this type where you compare different cuts in isolation, but not, to the best of my knowledge, where you actually compare different proof systems and see if you can simulate or separate them. So this would be interesting to study, but we don't really have the tools for this. And then the third and final and best question is somehow, well, it tells you that you really don't want to be in this column. But the point is we don't have really good heuristics for when would you do general linear combinations. We only know sort of in our algorithms, the linear combinations arise naturally because you want to cancel a variable. And we just don't have a very good intuition for when you would do general linear combinations, or even a good algorithmic intuition for how we would recover cardinality constraints, how we would recover from bad CNF encodings. There has been some work on this, but nothing that works really well in practice. Okay. So this is my introduction to cutting planes. And this might be a good time to consider taking a break. And then in the second half, we'll try to sketch the, we'll go over the interpolation lower bound, but it's really quite nice and clean and simple. So I think we should be able to do it in, well, I don't promise that I can be as quick as we were yesterday, but also I won't keep going till 6 p.m. Any questions before we break? Then let's have a 10-minute break. We're switching gears back from cutting planes as used for pseudo-Boolean solving to interpolation, which is what I promised to talk about today before I got completely sidetracked by pseudo-Boolean solving. So we already did interpolation. Let's do a super quick recap. So what's the idea? Suppose we have an unsatisfiable, you can think of it as CNF formula, or you can also think of it as a collection of linear inequalities. That's really what it's going to be today. But we know that we're a little bit schizophrenic in that any CNF formula we can also view as a collection of linear inequalities, as we saw before. So we have a bunch of P, Q, and R are different sets of variables. And we have a collection of constraints A over P and Q variables only, and a collection of constraints B over P and R variables only, and it's unsatisfiable. Then an interpolant is a function of the variables P only. Okay? That is the following. If I plug in rho throughout this talk, this lecture will always be an assignment to all the variables in P. So note that when I assign P by using rho, then this formula, just all the P variables will disappear and the formula splits in two. And if it's unsatisfiable from the beginning, then clearly it's unsatisfiable now also, but now we have two completely disjoint formulas. So at least one of them is unsatisfiable. Maybe both, but at least one of them. And an interpolant is something that points me to at least one unsatisfiable subformula. So if the interpolant of the group when I plug in rho is 0, then that should guarantee that the A part is unsatisfiable when I plug in rho. If the interpolant says 1, then the B part is unsatisfiable. Now, if both the A part and the B part is unsatisfiable, then the interpolant gets to choose. We don't care. Okay, so any function satisfying this is an interpolant. And now, for proof systems that have so-called feasible interpolation, we can do the following. So the idea is, okay, let pi be a refutation of these constraints. And suppose I can show that I can take the proof pi and somehow build from it a circuit of some shape or form that actually computes this interpolant. This is the feasible interpolation. Somehow, and this process is efficient in the sense that I end up with some kind of circuit of size that is essentially the size of the proof. Okay, what do I mean by the circuit? It will depend. We'll get to it. Okay, interpolation there are some parameters that depend on the proof system. There are different types of interpolation for different types of proof systems. But suppose that this process is efficient. So now I have some kind of circuit that computes the problem. Now, step 3. Suppose I can actually show that, well, any circuit computing this particular problem has to be large because it is a hard problem for this type of circuits. Okay. Well, so then now I know that the interpolant is apparently a very large object. But the interpolant is roughly the size of pi, which was an arbitrary refutation of this formula. So hence, any refutation of this formula has also to be very large. Has to be very large. Okay, this is, and remember, what did we do for resolution? So for resolution, we did interpolation. And we got standard Boolean circuits. Okay, now if you know your computational complexity theory, you realize that this is not terribly helpful because we don't really know how to prove lower bounds for Boolean circuits. So there was one other thing that we needed. We needed something that is called monotone feasible interpolation, which basically says that if the P variables only occur with one side, if they only occur say if they only occur positively here or only occur negatively here, then actually this circuit that I built can be made monotone in some sense. And for resolution, we show that indeed for any formula of this type, we could interpolate to get a monotone Boolean circuit. And then if this problem was the right type of problem, we could plug in a Boolean circuit lower bound. Okay. And for cutting planes, we are going to need also monotonicity, but we're going to need a stronger circuit model, which I'll define by picture, I think. We're going to have so-called real circuits. Okay, so and then let me tell you in a second what I mean by this. I think. Yes. Okay. Good. So for cutting planes, it's going to be different. I need to tell you about the new circuit model, which is real circuits, which actually on the wires of a real circuit. So let me actually write it down here. So we have some kind of inputs, and then we maybe have an output. So it looks like a circuit. And then we have, like here, we have a bunch of inputs. And here are like the variables, x2, x3, and these are Boolean, x5, x6, 7, whatever. But on these, all the wires in the circuit were actually sending like real valued numbers in arbitrary infinite precision. Okay. And then this final gate is sort of responsible for somehow thresholding to output to 0 or 1. Okay, so we're going to define some kind of computational model of this sort, and then we're going to do interpolation for it. That's our plan. Okay, what's the formula we're going to use? Well, we're going to use the clique-colouring formula. And I actually cheated a little bit. Let me tell you, if you remember what it was. So what's the clique-colouring formula? It says, the clique-colouring formula says the following, that there is an n vertex graph. There's a parameter n and a parameter m. There is an n vertex graph such that I can find an m clique. There are m vertices in this graph that form a clique. But I can also color the graph with m-1 color. Okay, and I can write this in CNF. It's a little bit annoying to write this CNF encoding for cutting planes, and cutting planes can massage the formula to a nicer form to have not quadratically many clauses, but to actually have cardinality constraints, and this derivation can be made efficient. So without loss of generality, we're going to work with this form. If you like the CNF form that we did in one of the first lecture better, then we can translate in cutting planes back and forth between that representation and this representation in like polynomial length. So any lower bound for one of the representations has to apply for the other also. Am I making sense? So this is my preferred encoding. So there are going to be variables q, ki, which basically says that I ranges from 1 to n. These are vertices. K ranges from 1 to m and identify clique members. And we say here that for every clique member k, some vertex I is that clique member. Okay, so QKI identifies, it says that yes, this vertex I is the kth clique member. And I need such a vertex that shouts out for every clique member from k goes from 1 to m that says, yes, I am the kth member of the clique. And then I say also that any vertex serves as the kth member for only one k. This is what this says, I think. And now here comes the condition. Like suppose, so it must hold that Pij minus Qki minus Qk prime j greater or equal minus 1. So this says that either, when is this satisfied? Well, either if I or j is not a member of the clique, then this is 0 and we're good because we have at most 0 minus 1, which is at least minus 1. But if both I and j are clique members, then there has to be an edge. So Pij are indicating that there's an edge between I and j. So if both I and j are clique members, there has to be an edge. This is what it means to be a clique. Then here the R variable says that every vertex I has a color L, where L ranges from 1 to m minus 1. So this enforces that every vertex gets a color. And then we say that minus Pij minus RIL minus RJL greater or equal minus 2. Again, suppose that what this says basically, suppose that there is no edge here, then we're fine, because then we have 0 minus at most 2 is greater or equal minus 2, so we're good. But suppose that Ij is an edge, then it cannot be that I and j both get the color L. Are we fine? This is kind of morally the same clique coloring formula that we had before, if you remember. And now you sort of do the translation, and you see that this is indeed a formula on this form. And furthermore, let's look at the p variables. We see that indeed they're only positive here, so that's great. And they're also only negative here. We only need one of these conditions, so here we have both. And this is like the one formula for which we have interpolation. I should also say that there is interpolation for another formula family that's called broken mosquito screens, which is kind of cute if you want to read on it about it. This is by Haken and Cook. So Steve Cook of NP fame, and Cook as in defining proof complexity in the Cook-Grechow paper, and Haken is the pigeonhole principal resolution Haken. So I'm not going to tell you what the broken mosquito screen is, except that you can write down a set of constraints in the same form and then run essentially the same machine, just for completeness. Okay. Good. So let me tell you what real valued circuits are. So basically, we have this circuit. The circuit is a DAG. It has constant fan-in. And let's insist on fan-in too, just for simplicity. It's not really important. The fact that it's constant is important. Okay. And now, every vertex V here gets labeled by an FV that is of any function from R2 to R. Okay? So I can just build my graph, and then I plug in any vertex. I just label it by any binary real valued function, except that it should be monotone if I want a monotone real circuit. Okay? If it's an arbitrary real circuit, then I could have any real valued function. Now I insist that it's monotone, meaning that if I increase, in the sense that, if I increase any of the parameters, the output cannot decrease. The monotone in the meaning of the word monotone. Yes, we're happy. So this is a monotone circuit. So again, we're feeding it with Boolean variables down here. Then we have completely crazy real valued functions. And then we have an output function, and the output function is responsible for thresholding so that it's outputting 0 or 1. At least on, like I insist on, if I feed it with 0, 1 values in, then I want to get 0 out, 0, 1 out. I could also feed in arbitrary real valued values here, and then for the output gate, I even don't care what happens. But I want a real valued, a real circuit. If I feed it bits in, then I get bits out. That's the only problem. Okay. Good. So question like, how powerful is this? Well, it's at least as powerful as a standard circuit. Like a monotone real circuit is at least a monotone standard circuit, right? Because AND is just min and OR is just max. And these are Boolean functions. And note that if I feed only bits in and then I do just min and max, that's going to guarantee that I get a 0 or 1. Yes? Okay. And the question is, so, but can they be more powerful? And the answer is yes. So it's known that there are linear-sized real monotone circuits for functions. The computing functions that if you want to do them with monotone standard Boolean circuits, they require exponential size. So linear versus exponential. Okay. The only slightly weird thing is that this is like an existential counting kind of argument. So we don't know of any explicit function, we just know that there are such functions. Okay. If you really care about this, then you can look at formulas. What's a formula? A formula is something where the circuit is now tree-like, so no DAG edges. And for if you look at formulas rather than circuits, then we actually do have explicit separation. And this is we won't talk about this, but this will follow from one of the papers that we will talk about later in the course. So, are we happy with real-valued circuits?
So
yes.
Is it even clear that like a function that you can compute in this way, that it is like computable in the traditional sense? Because this FR could be something completely crazy. Maybe just the monotonicity is.
Well, again, my promise is that if I feed it bits in, then I'm going to get bits out. So it is a Boolean function, right? I only care about Boolean values. And you know, any Boolean function, any monotone Boolean function is obviously computable by the DNF formula.
Right.
So I mean, for arbitrary real values, the Boolean model doesn't even make sense. But for bits, so I'm saying I'm forcing this model for bits. Like if this doesn't output the bit, then it isn't a valid circuit as far as I'm concerned. But it can be, again, it can be much more powerful. Which sort of tells us also that you know, getting lower bounds might be much more challenging. Okay. So we won't really talk about the lower bounds, but it just so happens, like the miracle happens now, that what we did is, for resolution, if you remember, we appealed to a lower bound by Razborov that said that distinguishing like cliques was hard for monotone circuits. And it turns out that Razborov's lower bound technique is so general that it actually lifts with some effort to this model. I don't think we will have time to talk about this. And we could do it like at a separate lecture at some other point if you're really interested. I would be happy to do it. But in this course, we just decided there's so many things we want to cover. And the fact that there's a lower bound, this is really not proof complexity any longer. This is circuit complexity. So I won't do it today. We'll just use that Razborov's lower bound for standard monotone Boolean circuit just lifts to this set. And this is like, and then Pavel Pudlák is modest in his paper and says, oh, this is obvious, but let me just, you know, write down the details for completeness, and you know, and then the reader may judge whether it's obvious or not. I think it requires some work. But it's a very nice observation. I mean, particularly the observation is super nice to realize that like this is the model and here's our circuit flow. Okay, we're happy with real-valued circuits. So then let me tell you what the interpolation theorem is. So in brief form. So let's suppose that we have a bunch of inequalities that look like this. So for p living in the p variables, we have a linear combination Cp times p. And then we have Ci, sorry, there should be an I also. Cip times p, Ci, q times q variables greater or equal di. For a set of indices I in capital I. And then we also have linear inequalities for p in p, and for this was for q in the q set. Now I guess we have Cjp times p plus for r in the r set, Cjr times r greater or equal dj, or j living in the j set. Suppose that these are inequalities, and let P be a cutting planes refutation. Of this. And again, the P, Q, and R are now disjoint variables. Let W be max number of P variables in any inequality. So in particular here we have W1, yes? Only one P variable in any inequality. There could be more, of course, but there's only one here. And suppose all Ci, comma P are non-negative, or all Cj P are non-positive. Then there exists a monotone real interpolant of size, which is the number of vertices, at most W times the length of pi. This is what we want to prove. Clearly, if we can prove this, and then for the clique-colouring formula, and if you believe my claim that Rasborov's lower bound lifts to this setting, then we should have our lower bound for this. This clear? And we actually, with W being 1. Okay. I could say one thing more. What's this business with monotone real circuits? Suppose I give you an extra promise. Okay? Suppose that I promise to you that in the proof, all coefficients are of at most polynomial magnitude. Meaning that all coefficients have at most a logarithmic number of bits. Then actually you can do this interpolation with a bit of a blow up, but you'll get a standard monotone circuit. Okay. So this says that, and there was actually such a result before, I think by, okay, this is dangerous. EPR is this. This is Pitassi and Ras. And Bonnet, Pitassi and Ras. Blackboard syndrome. That you can go, so like if you promise to me that you're cutting planes with coefficients of at most polynomial magnitude, then there was a lower bound before, and you can do it with standard interpolation. You need to manage the blow up a little bit, and then Pudlák said, no, let's look at general cutting planes where I don't have any bound on the coefficient. So in general, I don't remember if I said this or if I forgot to say this. When you look at cutting planes, you look at the coefficient size. I think I said it. So in general, coefficients can be arbitrarily large. There is a result that says without loss of generality, except for a polynomial blow up with respect to size, you can assume that polynomials have at most coefficients have at most exponential magnitude. I'm not saying what happens to other measures such as space, by the way, but at least if you're only looking at size, then without loss of generality, coefficients are of at most exponential magnitude. Cutting planes with polynomially bounded coefficients is sometimes referred to as CP star. So Bonnet, Pitassi, and Ras had a CP star lower bound. Pudlák gets a general cutting planes lower bound. We don't know, this is a great open question that we will also talk about a little bit later in the course. We don't understand whether cutting planes with exponentially large coefficients is stronger with respect to size than cutting planes with polynomially bounded coefficients or not. In fact, the paper which is usually credited with showing that coefficients are of exponential magnitude without loss of generality, Bas-Klote, they were actually, it was very clear in the paper that they were shooting for getting coefficients down to polynomial magnitude, but just didn't manage. So it's reading that paper, the sort of the intuition is that why would you need anything more than logarithmic number of bits, more than polynomial magnitude? Now I think the intuition is not so clear. We'll see hopefully a result later in the course that suggests that at least there are some things that you can do with arbitrarily large, exponentially large coefficients that you cannot do with only polynomially large coefficients. Okay, so this is the interpolation theorem. Are we happy with the statement? Then the proof is like going to be super straightforward. So in some sense, we're just gonna, I'll tell you what the idea is, and then all we need to do is just boring calculations to check that this works out. That this works out. So, and the idea that we're gonna do is gonna be similar to resolution, but remember for resolution we sort of have to classify the variable, the clauses as either Q clauses or R clauses. Q clauses were the one that came from this part, and the R clauses were the one that came from this part. Now we're using the fact that a linear inequality is a more general object. We can just split it up in two, in a sense. Okay. So suppose we have any line in the proof. Any line in the proof looks like this: Cp times P plus CQ times Q plus CR times R, and this is again summing over. I probably won't have the energy to write out these indices. Let me write them out like one final time. So when I write the sum, this is obviously summing over P variables, this is summing over Q variables, this is summing over R variables, a greater equal sum D. Okay? So now what happens to this guy when we hit it with a restriction? Well, this goes away, right? And we have this plus this greater equal D minus Cp times rho of P. This is like what the restriction does. And now what we're going to do is we're going to split this inequality into two inequalities. There should have been a C here, I guess. So we're going to write this as CQ times Q greater equal DQ, and CR times R greater equal DR. So morally, like I'm going to take this thing and just split it up into two inequalities. Okay? And then the question is, but what do I know about these guys? Well, I'm going to make sure that, and maybe let me write this here. So somehow the idea is we're going to have all the time CQ times Q greater equal DQ. And then we're going to have a CR times R greater equal DR, summing over R here, summing over the Q here. And then importantly, we're going to maintain the invariant that DQ plus DR is greater equal D minus summing over the P's rho. Sorry, I want the coefficient first. Cp times rho of P. So what does this mean? This means that I split them in such a way that if you're worried about losing information, then you say, well, I can just add them up again, right? If I add this and this, then here's my right-hand side. And then I make sure that when I add dq plus dr, that's at least d minus cp times rho. Maybe better, but at least, like, I don't necessarily claim equality, but I'm going to have at least. Okay? This is my plan. And I'm going to refer to this is like the constant term. So I'll call this sometimes maybe the notes will call this the Q term, and this is the R term. And now, suppose I can do this. Why should I be happy? Well, the final line is 0 greater equal 1, right? So then I'm going to get 0 greater equal dq, and I'm going to get 0 greater equal dr. This is how I'm going to split it. And then I know that dq plus dr is greater equal d, which is 1. Okay, and also since I will do this splitting, the way I'll do the splitting, I will actually just derive, this will always be derived from the Q part of the formula, this will always be derived from the R part of the formula. So I will run two derivations in parallel, and then I end up with these two inequalities. And this will do like incomplete generality, regardless of, we don't know what rho is, so we'll just do this derivation for any row, right? And now the point is that, well, if they sum up to 1, then at least one of them clearly is greater or equal 1. Maybe both, but at least one of them. So I can just look at these guys, and if this is 1, then I know that the Q part of the formula, the APQ part, was unsatisfiable, and if dr is 1, then the BPR part was unsatisfiable. Okay. So I just have to do this, and then in a final step, we'll need to convince ourselves that basically, so what does our monotone circuit need to do? Well, at the end of the day, if it could compute this for the final line, then we're happy. Am I making sense? Okay, but then this is all there is, right? We can kind of go home now. Except maybe we should do the inductive construction. But the interesting thing is that since we now have a much stronger circuit model, remember this was, I don't know if you remember, but I think for resolution, this was a bit of a pain. Okay, but it's not going to be, I already told you what we're going to do, and you can already guess how we're going to do this, right? The only thing, we need to split the axioms, and then for all other derivation steps, I mean, we're just going to run them in parallel, and we just need to stare at them and see if they're okay, and nothing's going to happen. Okay, why are we getting this for free? Well, I think one reason we're getting it for free is that we have sort of we're mapping into a more expressive circuit model that can do more fun stuff. Before we like really had to make sure that we could do and ors and stuff, and it was a little bit long. Okay. Okay, so should I stop beating around the bush and just do it? Okay, so good. So, and I have my invariance down here. This is going to be like the inductive invariance. Okay, so let's see how to do this. Maybe we can keep the whole proof on the board. Okay, axioms. This is the base case. Okay, so axioms means that we have now CP times P. Okay, it's the third one. CP times P plus CQ times Q plus CR times R. This was the original line, greater equal D. What could this be? This could either be a Q axiom, which for us in the clique-colouring formula is one of the first three constraints, or it could be an R axiom, or it could be a variable axiom. Okay, so let's just do a case analysis on the R variables. So case one, No R variables. Well, that means that CR times R, that linear form is just equal to 0. And we can set, so we'll just set, so the R part, we're just going to be, that is going to be 0 greater equals 0, which is not very fun, but I mean, we can allow, I mean, either we extend our proof system to allow this. I think strictly speaking, I didn't allow this, but either let's be more generous, or we'll just post-process away them. Okay, this is kind of clear that we should be able to get rid of this. And then I just the rest of the axiom will be the Q part will just be basically CQ times Q. And I just set that to be greater or equal D minus sum over the piece, CP times rho of P. Okay? And this is clearly just a restricted axiom. So that's fine. And this is fine. And we are maintaining this invariant with equality. Okay? And otherwise, well, if there are R variables, then we know there are no Q variables. So then we let the R part be sum CR times R greater or equal D minus CP times rho of P. And we let the Q part be 0 greater equal 0. Just the same. Okay. So now we have, for the inductive step, we have 3 cases. So addition okay, we're adding CP times CP prime times P plus CQ prime times Q plus CR prime times R. This was the original thing, greater or equal D prime. And we're adding C double prime P plus C double prime Q times Q plus C double prime R times R greater or equal D double prime. So by the inductive hypothesis, we know that we have dq prime plus dr prime greater or equal d prime minus c prime p times rho of p. And we have the q double prime plus dr double prime greater or equal d double prime minus d double prime p times rho of p. When we just did the splitting. Now it's kind of clear that, well, okay, we know this. So let's just see what do we do. So this is again restricted away, right? And now we just say, okay, so on the Q side, we get CQQ greater or equal D prime Q. Probably the primes should be up here. Sorry about that. So we're going to add for the Q part C prime Q times Q greater or equal D prime Q. And then we do C double prime Q times Q greater or equal D double prime Q. And we're going to add them. And then we get C prime plus C double prime q times q greater or equal d prime q plus d double prime q, right? And on the r part is going to be the same. So we end up with, so clearly this is the q part. You kind of see the r part is going to be the same. I warned you this was going to be boring. Okay, and now we just need to look at, so we're going to get this guy and a similar guy for the r. But we know that if we add d prime q plus d double prime q plus d prime r plus d double prime r, then that's going to be at least d prime plus d double prime minus this thing. But that just happens to be the exactly what we want for this new life. Okay. So basically, supposing that I had split before, I just do the addition separately. Multiplication is no more fun. So again, we have say c prime p plus c prime q times q plus c prime r times r greater or equal d prime. And let's suppose we now multiply by lambda because the c's are kind of occupied today. And we get lambda c prime p times p plus lambda c prime q times q plus lambda c prime r times r greater or equal lambda c prime. Okay, so what are we going to do? These are going to move over to the other side when we hit with the restriction. This is the q part. And this is going to be the r part. And we knew before that dq plus dr was greater or equal d minus this sum cp times rho p, right? And what do we want afterwards? Well, afterwards, we're just going to have lambda dq plus lambda dr. But I mean, what are we going to have on the other side? Well, we're just going to have that, yeah, I mean, we're multiplying through by lambda everywhere. So nothing really happens. Okay, so we're kind of done, almost. Let's see. Division. So again, if we divide it by lambda, and suppose for simplicity that we have this division rule that is even, then we know that we had lambda times cp p plus lambda cqq plus lambda crr, maybe leaving it as an exercise to figure out that it's easier to prove if we don't have this common factor lambda. So we had a division step, and now we just get dpp plus dqq plus crr greater or equal d divided by lambda, rounded up. And again, we see that clearly, and again, what did we know? We know that dq plus dr was greater or equal d. So in the split part, clearly dividing, if we have lambda cq times q, greater or equal dq. Let's just do that part. I mean, clearly I can divide here, right? I just get CQ times Q. What will I get here? Well, I get dq over lambda, rounded up. And the same on the other side. So again, clearly these are valid steps because I'm dividing here. And actually, I'm divisible by lambda, but even for the general Pudlák cuts, we would be perfectly fine. Okay. So now we just need to see that, are we satisfying? Now we need to see, like after the division, what do we know? So after the division, the new dq is dq over lambda, rounded up. And the new dr is dr over lambda, rounded up. And this had better be larger than d over lambda minus this thingy. Right? So let's see what we get. Well, firstly, this is clearly larger than dq, larger or equal dq plus dr over lambda, rounded up. Right? This can only get smaller if I add them up and then round up later. Okay, but then I actually know that by induction, these two guys are larger than d over lambda cp times rho p, right? This is larger or equal this. Let's divide through by lambda. Since this is larger than this, surely I can round up if I like, right? Okay, but now you realize that this is actually equal to d divided by lambda, rounded up. And note that here we just have even division. So this is minus Cp rho p. Which is exactly what we want. Except there is apparently a typo in my note because I forgot this lambda there, but I'm adding it now. And this is again, so this is the new d, and this is clearly this one. Okay, so what have we done so far? So this shows that we just split the axioms, and then we run two cutting planes derivations in parallel. And then we know that we can just look at them at the end, and for any concrete row, either the final dr or the final dq is going to be bigger equal 1, greater than or equal to 1, and then we know. Yes? Are we done? We need to show that this is computable by monotone circuit. I mean, you and I can see it with our eyes, but can a monotone real-valued circuit see? Yeah. So let's talk about this. Let me. Okay, no, I don't want to save anything here, I guess. So now there is a case analysis, and let us assume that I'll do one of the cases. So we said either all CPs are greater or equal 0 in the Q part, or the smaller equal 0 in the R part. Okay. So okay, so let's see. We want to build interpolating real monotone circuit. And again, the details are slightly different. So we're going to assume one of the cases, assume that P variables are only non-negative, non-positive in B PR. Okay. So then our plan is for every line in the original proof, we compute DR. And then we add a final threshold gate that just says it's going to be a single input, and it's going to be 1 if x is greater or equal 1 and 0 otherwise. Okay, so all I need to do now, clearly I can add this threshold and gate at the end, right? So all I need to do now is to build a monotone circuit that computes these DRs. Okay, so let's see. So if we have an addition of constraints, we have two constraints, you know, Ci and Ci prime, and we add them up to get C. Okay. Actually, Ci prime and Ci double prime, and we get Ci. Let's say this is the Cth line. Then in that case, obviously the Ri is just equal to dr I prime plus dr I double prime. This is a monotone function. So assuming that I've successfully computed these two guys, the gate corresponding to an addition step just adds up these two. That's an addition gate. Multiplication by lambda, well then I know that di is just going to be lambda times di prime. And now I think I need to argue, here's a corner case here. I think that in this, if you look at how the construction went, I'm only going to add and multiply and divide. So you might worry now that if if this dr thingy went negative, yeah, how did I write it? dir prime, then of course, if this is negative and lambda is a positive, then this is more negative. But I can sort of threshold, like I know if I hit 0, I can always just, actually I can like do a min, I can do a max, I think, of either 0 or lambda times d r I prime, I think. This also seems to be missing in the notes. I'm doing this a little bit online, but I think the point is, if I ever go negative, then I kind of, then and there, I know that the R part is not what I'm looking for. But just to go through with the definition, let me do this for multiplication. And I think this is okay. If I leave it as an exercise for you guys to check if this is correct. And then we have division. And division is going to be like, say that di is some di prime divided by lambda and then rounded up. Well, then we know that dr I is going to be dr I prime divided by lambda rounded up. This is definitely a monotone function. Okay, so now I showed for every division and multiplication, division, multiplication, addition step. Addition had two gates feeding in. Multiplication and division are unary gates, and I have arbitrary real valued monotone function. And note that I'm using, like here was when we had to do this selector gates and classifications and stuff, but here I can just, my gates can just compute these numbers. Okay. Are you kind of with me so far? On a good day? Or cutting me some slack? Okay, so the only thing is now, okay, good, but how do I compute the axioms? Right? Okay, so what about the axioms? Well, there are two cases. There are axioms without R variables. What did we do with those? Well, then the R part was 0 greater equals 0. So we just have the constant 0. That's easy to compute. And that's fairly monotone, like in all senses of the word. Okay. But suppose we have an axiom with R variables. Conveniently, I erased what we did, but remember, okay, so maybe a quick recap. So what did we do? We started with Cp times P plus Cq times Q plus Cr times R greater or equal D. This was like the original, but then we said, oh, but this, if this is an R axiom, then we know that there are no Qs. So these guys don't exist. Okay, good. And also this was restricted away, right? So this goes over here. So we get Cp times rho of P. And note now that this is actually this is a constant, and this depends on rho. So this is just the value, basically, rho gives the P. This is it. Okay. So this takes care of this. So, and then we said that the Q part. So this was actually then this was the R part. Like the board is getting messy. The R part, when the dust settled, was like, it's going to be this inequality. And in particular, this guy is dr, which we want to compute. And let us just recap that the Q part here, which we don't really care about, but just for completeness, here the Q part was 0 greater equal 0. So that's how we mess things up. Okay, so all we need to do now is to compute this guy as a function of rho. With a monotone circuit. And here is where we're going to use the promise that all of these guys are non-negative. So this is actually plus minus this. Okay. So this is a number which I can just hardwire into the circuit. This is a positive number. This is a plus. And here I just sum up the values of the rows. Note that here, if I have rows of p's, note that if I have many p's here and then I insist on binary span-in, then I'm like going to have I'm going to need a sequence of gates to sum these guys up, right? That's where this Where did it go? This is where this W comes in, right here. But actually, I mean, it's a very stupid bound if you think of it. But... And since I know that CPs are non-negative, minus CP are non-positive, minus CP is non-negative. So this thingy is a monotone function of the p-variable. So we're fine. Questions about this, or should I say it again backwards? We're happy. So again, and now if you realize, okay, what if we're in this case instead? Well, then you then you're just gonna deal with the. I don't even remember if the details changed or somehow. Like actually in the I think in the resolution part we never did. This is like the case we didn't do for resolution. And in resolution the patches are slightly different. I don't remember if they're maybe slightly different also. So in particular, I think the way we did the splitting, maybe we sort of did it. The way we split up the axioms, we kind of know that the R part is going to be the non-positive part, I think. And if we're in this case instead, then you're going to do something slightly different with the axioms. But then like all the inductive steps are going to be exactly the same. Okay. So this, I claim, shows Pudlák's interpolation theorem. And then you will have, let me say something extremely brief, maybe just to sort of tell you what the circuit lower bound looks like. So let me try to do this in like 5 minutes. So you're going to do something like the following. So we're going to find some family of simple functions f, okay? And here is how, so we're now assuming that we have, now we're looking at, in particular at the clique problem where we have monotone circuits. That looks something like this. It looks suspiciously much like a pyramid, but that's just a coincidence. So the idea is, so all dictator functions, so all functions that just take n variables and project out, all I cared about is the value of x42. All of them live in F. And that means that the inputs here, I can approximate them well. Or I can compute them exactly. Okay. And then for every gate here, I somehow argue that I'm able to approximate it with a small error. So somehow, you know, these gates are 100% okay. And then I pick up maybe some small error here, maybe some small error here, and maybe some small error here. And once I picked up that small error, I'm sorry, that's just going to propagate. So I, you know, kind of lose a bit. Actually, maybe these are even, sorry, let me do different colors. This error propagates like here, and this error propagates also here. And this was a blue error, and that blue error ends up there. And then these two circuits maybe, so the red error and the orange error and the blue error kind of propagate up here, but there are some new errors. Maybe this guy introduces some green error, for instance, but it's like all of these gates are approximated in f almost correctly. Okay, so for every single gate, you're just incurring only a small error. And then you just argue, what is this circuit computing? Well, it's detecting a clique. And then you look at the functions in f, and you realize that the output function cannot be approximated well by any function in f. So we're saying like this function must be true. It's a disaster. Okay. So now what do we know? We have perfect computation here. Every single gate incurs very, very small error. And here it's like complete and utter chaos. How could that have happened? Well, the only possibility I went from perfect and with excellent approximations all the way to chaos is there must have been tons of gates, no? Because otherwise, how did the errors accumulate so badly? Okay, and now all that remains is like a lot of blood, sweat, and tears to actually make this work. The Boolean case is not so bad. We sometimes do it in the computability and complexity course. So, you know, if you want to see it and want to do some lobbying, then try to convince me that we do it in Coco this year. We might do it. And once you've seen the Boolean case, it's not so hard to then, like if you really understand the Boolean case, then you work a little bit harder and then you do the real value case. And I think this is what I wanted to say about this. And so since we will get lower bounds for interpolating real monotone circuits for this function, this tells us, for cliques, this means that these clique-colouring formulas must be exponentially hard for cutting planes, regardless of how large coefficients. So open problems. We're going to see, like, interpolation requires very, very structured functions. So for instance, if you think about, you know, a random KCNF will absolutely not have this structure, right? So we need, like, what are techniques to deal with random KCNF formulas, for instance? And are there any other techniques than interpolation? Again, we will see, but this is still a very active area of research. We'll see a fairly new way of doing a lower bound for random CNF formulas, except it's not how to do it for not known how to do it for constant width. For logarithmic width, it's know how to do it. That's by Noah Fleming and others. But that's state of the art. Like going beyond logarithmic, below logarithmic, we don't know how to do it. And then, as I said, we're going to talk about communication complexity and lifting theorems, which is also a very active area where, in particular, you take a fairly large hit in the parameters because the lifting makes the formula much larger. It's an active area of research to try to get much, much better parameters, which would lead to, there are some type of results where you really want, like, the blow up not to be so bad. And then, as I told you before, a number of questions for more algorithmically motivated cutting planes. Can we understand if I start playing with division or saturation or so-called mixed integer rounding cuts or some other cut rules? Can we compare the strength of cutting planes with different cut rules? And can we come up with a good idea to do non-canceling linear combinations and to recover from bad CNF encodings? And one very concrete problem, can you come up with a family of linear inequalities where cutting planes plus this saturation rule, which operations research people also call coefficient tightening, could it be that cutting planes with saturation / coefficient tightening can be better for certain types of formulas than cutting planes with division? That's it for today. Any questions before we wrap up? So then I think we're done.